Well, multidisciplinary, yes. Well, I suppose I'm approaching this from the point of view of social simulation, and there's obviously an epidemiological modelling community, which many of you are members of, and I'm come from a rather different community, a social simulation community. And my feeling is that they've had almost no interaction. And so I want to put forward a view of a different way of thinking about all of this, different paradigm, if you like. And hopefully, as a result, there'll be some meeting of minds. So as we've already heard, you know, the epidemiological community is on the whole dealing with large-scale, data-dependent, differential equation-based models. And in contrast, the social simulation community, which is made up of computational social scientists largely, and deals with relatively small-scale models, ones where I put here theory dependent, but conceptually dependent is probably the right, perhaps the better word, but I'll illustrate that in a moment or two. Agent-based models of individuals. Now, as Mark has said, that there are already individual epidemiological models, but one of the points that makes, that differs here is the notion of an agent as opposed to an individual. And again, I'll talk a bit more about that too. I've just, to put, in order to put something graphic on the screen, I've extracted a picture from the London School of Health and Tropical Medicine model on the left-hand side, and an agent-based model of the pandemic on the right-hand side. And one of the things that you'll see on the right-hand side is there's a lot of sliders, a lot of parameters they represent. And we'll talk a bit more about that notion as well in a moment. So what we start off with our social simulators is the rather obvious statement that society is complex. And to a large extent, this community is very well linked into complexity science. And this brings forth some requirements for the kind of modeling that we feel that is needed. So and much of this will probably be very familiar to you. So social phenomena tend to be highly non-linear. So an epidemic is, of course, an extremely good example of that. There are feedbacks and tipping points, so that change takes place slowly at first, but then can get to the point where there's to the point of no return. And we have many illustrations of that with our pandemic, or likely illustrations. The notion of emergence is extremely important in the social sciences, sometimes not actually described as such, but emergence is a good way of thinking about it. Emergence where we have higher level properties arising from lower level interactions. Clapping for the NHS every Thursday, which is one, or indeed the Isaac Newton Institute is another emergent organisation arising from the effects of the individuals who make it up. Obviously, people adapt, they learn from their experience, from the media and so on, and importantly, they may act strategically. So they think about the future as well as the past. Panic buying of toilet rolls, as an example. And then multiple scales, and I'm talking about a complexity of society, but we could also think about the complexity of individuals, of households, of organizations, of nation states, and so on. So how does the social simulation community deal with all of this? Through agent-based modeling. And agent-based modeling is a very simple idea. What we build is computer models that incorporate individual agents that interact in the computer, as it were. And importantly, these agents are heterogeneous, as indeed people are. Equally importantly, that these agents carry out actions. We represent them, we simulate them carrying out actions according to some specified set of mechanisms. I should talk more about the mechanisms in a moment. So we have individual action, and we also have individual level interaction. And this is model 2, and this is one of the ways in which agent-based modeling, as the social simulation community does it, is radically different from almost all of the, as it were, standard epidemiological models, which some of which do have representation of individuals, but they don't interact in any meaningful way. Also, I might say that when I'm talking about mechanisms here, I'm explicitly not talking about things like transition matrices or probabilities. We're actually representing what people do, as we shall see in a moment. And we can also represent culture. The people in the culture of in China is very different from the culture of the United States in relevant ways for modeling pandemics. We can model the media laws, the effects of regulations and so on as constraints on individuals. And we can even model adaptation, so that agents can change their behaviors in response to changes in the environment, and they can, in the more advanced models, learn using genetic algorithms, imitation, and other such things. When I keep talking about mechanisms, I put up this as just a very simple example. I'm not saying that this is the ultimate, but just to, as a way of thinking about this, this is in fact taken from a rather old paper about modeling epidemics, in which the agents in the model follow this kind of flowchart. And of course, they meet with other agents in the model when they're at work, in their household at home, and so on. So this just shows you what I mean when I'm talking about individual level rules and individual level interactions, all of which build up to an emergent phenomenon, that is the epidemic. So these agent rules, each agent is in a context of other people, of the family, the workplace, or whatever. They follow some kind of mechanism, which may be much more sophisticated than what's illustrated here, with some kind of outcome. In order to model these kinds of mechanisms, we need data. We need data about individual motivations and perceptions. We need data on their daily activities. We need data on demographics, and we need data on their context, household, employment, and geography. I think one of the things you might be thinking now is, well, all this sounds very good, but where do we get all this kind of data from? Much of it actually is already available in one way or another. I try to indicate some of the sources of these kinds of data. A lot of this data needs a great deal of work to get it into a form that makes it suitable for this kind of modeling, but it's not impossible. to obtain, given enough energy. So we could, in principle, build, I would argue, an epidemiological ABM, and one that has the same kind of objectives as the imperial or the LSHTM ones in terms of scale. But actually that isn't feasible in the short term because it would be a huge amount of work. So why am I talking about agent-based models if it's not something we can do? Actually, agent-based models work not just at these very big scale, but also at the small scale. We can build small, quickly built agent-based models that are limited in scope and that are ways of trying out theories, trying out hypotheses, not doing forecasts, not doing predictions, but suggesting what kinds of factors might possibly be important to act as kind of thought experiments. And these can be helpful to communicate with both the public and with policymakers to illustrate the effects of uncertainty, not in a statistical sense, but because we can vary parameters on these kinds of simple models and see the extent to which we get different answers. And we can allow the simulation of specific policy scenarios. So here's just one illustrative example of the kind of thing that I'm talking about. This is in fact a model that developed in the University of Hohenheim. It's not a sophisticated epidemiological model, but it does allow users, and it's now available on the web, so that the user can be anybody, to examine the effect of choices, the sorts of things that are shown on the right-hand side. You can vary, and you can actually see the agents in the model moving around this townscape as time goes on. If I were being brave, I could actually demonstrate that to you. Perhaps I'll see what happens if I do that. You can still see that? There we are, you see. So there's the agents, little green dots.
So the screen sharing is locked on your slides, so unfortunately we can't.
Right, okay. I will see whether I can do that.
You may have to.
No, it doesn't look like I'm going to do that. Anyway, you can't see the little agents running around, but never mind. I'm sure you can imagine. So what should we be doing? In the short term, I want to suggest we should be building small agent-based models, limited and specific policy relevant issues. And the three that I've listed there are all things that would be relatively easy to model and indeed are being modeled by colleagues. In the long term, I want to suggest that we should be preparing for the next pandemic, and that now is the time to start thinking about building what I want to call a digital twin. There are digital twins, if you haven't come across this notion. It was originated in I think in planning, in building works, and where you basically set up a virtual copy of, let's say, a skyscraper, including all the physical parts and the internal temperatures, internal environment, and so on and so forth, so that you could investigate as an architect changes, and it also helps with maintenance of the building and so on. What I'm suggesting is that what we should be thinking about as a major challenge, almost a grand challenge, is to build a social digital twin of either a city or the whole of the UK. Both of those are possible. but major, would require major investments, so that when the next pandemic comes, as it surely will, we will have a virtual society in which to try out different policy possibilities. Here are some further links to further examples of agent-based models applied to the pandemic. These are just 4 of the ones that I'm aware of and are well developed. I'm quite sure that there are others. And finally, there's a couple of articles that you might be interested in if you want to pursue this further. And that's my brief introduction.
Fantastic. Thank you, on the spot on time.